Got a lot of questions, so why don't we get right to it? Let's see. Today, more and more new materials are being created that are lighter, stronger, and more difficult to machine. One bottleneck machining new materials is older cutting technologies. Are your companies considering game-changing technologies like cryogenic machining to cut new materials more efficiently? Okay.
Well, we do a lot of machining. I
Yep.
think what people don't recognize is that Alcoa, which is now a collection of Firth-Rixson, RTI, and Total, so more than aluminum. RTI alone was a diversified manufacturer. We had machining capability in Minnesota and Montreal. So it's clearly recognized in the space of titanium. It is a problem. All the things that you love about titanium, it's tough, it's strong, it's temperature resistant.
So let me give a variation of the question.
Yeah.
In my role as moderator. So in the early '90s on the F-18, we went to high-speed machining. That was kind of a revolution. A lot of parts, a lot of complex parts we could make. So where do you think machining's going in the next 20 years? I'm asking an additive person that question. Where do you think that's going? Do you think there'll be more advances? Do you think you'll see less of it, more of it in the future? Or what are your thoughts?
I think there'll be more advancements, and I think the change, just like we moved to composites, which then drove changes in the way that we developed cutters and things like that. So that those things still required machining. It also drove more titanium, which then caused us to look at the problem. I think additive is interesting because it doesn't eliminate machining at all. It just changes your strategy for doing machining. So whereas before you might have been thinking about taking massive cuts of titanium, maybe now it's going to be a lot of finishing.
Yeah.
So that's personally, I think, the way. I think it's just going to move the problem around. So I think it's still exciting for engineers because there's lots of problems to go solve.
Yeah. I see a combination of near net shape, additive, and some finish machining. Maybe that'll transition as time goes on, but I think that is an area low-hanging fruit, personally.
Yeah.
So, okay, so here's an interesting question. Nirvana would be to significantly decrease material development to a material allowables time frame, but when you can't do that through computational means, how will you convince the stress analysts that computational models were correct without testing thousands of specimens? So this is the chicken and the egg thing.
So it really gets down to verification, validation, uncertainty quantification. The same stress analysts now use CAD and finite element analysis and don't have any problem. Yet if you go back 1985, a lot of guys wouldn't get on the computer and would still wanted to do hand calculations. So I think there's hard work involved in getting those models to that reliability and that confidence level, which is based on testing. So eliminating tests I don't see is ever going to be a case, but the ability to believe those models really gets down to the verification, validation, uncertainty quantification.
Okay. This question is, thank you, Mick. This question is directed to you, Mick, and to Dr. Vaya. Will we see more atomic structures engineering beyond the nano in the next 20 years? What is your vision, prediction of what it will look like? Okay, I think we kind of touched on that a little bit.
Yeah, that's an excellent question. When Nano came on board 10, 15 years ago, that was the vision. We would be able to build everything atom by atom. I think if you do simple back-of-the-envelope calculations of the number of atoms you would have to do to create something macroscopic, you quickly realize that the time scales don't match. And so I think one of the things we've been thinking about in partnership with DARPA over the last year or so is that maybe the solution is not going from the atoms clear to the airplane, but looking back on how we do manufacturing today, you can kind of assemble things over roughly a couple orders of length scale. And so how do we assemble things from the atom to the micron scale to create feedstocks with which then we can feed into existing processes to go from the micron feedstocks up to the macro feedstocks? I don't know what those actually will be, but I think breaking the problem down that way is going to help us move forward to better understanding or realizing some of the potential opportunity space that's been promised for the nano world.
So yeah, I go back. I think it's the control aspects, being able to control at the molecular level, the processing you use to get there. Like you said, being able to move from atoms to micron units that can then possibly do self-assembly to get a structure kind of in the time scales is what matters. But again, it's the control getting at that level, I think, is what's going to enable new materials. The big thing that I found as we've moved down in scale, going to nanometers, to atoms, as material scientists, we're able to talk about that relatively fluently amongst ourselves. But when you go to talk to the people that are going to be the funding, that want to fund that kind of work, they really don't care. They care about the airplane wing. They don't care about you being able to move this atom over to here or that kind of control that's the enabling technology. So that's there's going to be pluses and minuses as we move down that scale.
Okay. Interesting question. If you had $50 to $100 million to invest, Mick, everybody, in one materials development process thing, what would it be? One project for that kind of money, what would you do?
So that is a DARPA program. So I'm a composites guy. Since I've come to DARPA, I've been handling a lot of their manufacturing and composite material programs. So if I were to have the $50 to $100 million today, I would put it into what my new program is, which is basically looking at a tailorable feedstock to support small composite fabrication.
Okay. All right. And any other thoughts?
I think similar. We just recently launched the Flexible Hybrid Electronics Manufacturing Institute, which is roughly on that scale.
Yeah.
And the reason we're very bullish on that is that it's putting a path forward where you can take the exquisite functionality information processing that you get from a silicon foundry and actually be able to envision ways to put it into a composite or integrate it into the emerging manufacturing processes, which are layer by layer, in a manner where you can retain mechanical properties, but now you're embedding silicon fab functionality in it. And I think that's a really exciting opportunity space moving forward.
All right. All right,
think-
thank you.
Can I?
Yeah, John?
I actually would go back to additive manufacturing. I think that there's huge swaths of value which haven't been reached yet, from how you tie just the act of 3D printing into the supply chain, into the value chain. And then, if you look at the machines that are made today, they're built on an average premise. So if you feed Ti-6 4 parameters into an RCAM machine, it gives you an average for a shape and a requirement. So, my personal belief is that, and it holds time as a constant, but we can change those parameters as a function of the build if we want to achieve, more value out of that print. So I think we've only just, in some cases, GE having the success with the fuel nozzle was a curse and a blessing, because everybody thinks, okay, well, we're done here. We'll just move on to the next thing.
That's right. Reduce the practice.
Yeah.
Right. No more development. Yeah.
So I can't pass up spending $50 million either.
Yeah, go ahead, Tom.
So if I was going to spend $50 million.
Trust me, I know that for personal experience. Yeah.
But it's not going to be the same answer I usually give. This is one where, just playing off of what we're talking about today, and where these different material systems have been, the things that have come and gone, and the influence that we have on material science, I would draw back even further and say, a lot of times I find, especially for new materials, we're fighting physics, we're fighting entropy, we're fighting the things that where we have to manufacture around. And what was that? You can't fool Mother Nature? We got to understand physics-based modeling. We need better physics-based models for how materials perform at the very small scale, so that we're able to integrate that up the chain. And I think that impacts everything, from whether it's a nanomaterial system, whether it's how we're doing additive, whether it's how we're able to predict performance of a material and move forward to do virtual testing. I really like the answer to the 50s. If I had $50 million back in the day, I would have just said, hey, let's build another X-15 because we learned so much on that program. But an X-15 today is a $500 million program. But when I talk to people who worked the X-15 back in the day, their comment was, oh, it was the heyday of materials because you could goop some stuff up, you go out and you put it on the wing, you fly it, and then you see how it performs. And then you go back and change your formulation. And it's like, if we understood the physics better, and if we invested that up front, and grow our workforce while we do that,
Yeah, you'd have fewer iterations, right?
we would now be able to bring that directly into our business.
Yeah. Okay. All right, good answers. So Todd, I got 2 questions I'm going to combine to one question for you.
Okay.
CMCs. What makes CMCs suitable for aerostructures? What parts of the aircraft are you talking about? And basically, what makes CMCs suitable for repeated thermal cycle, duty cycle applications?
Oh, yeah.
Good questions.
I'll try to hit that. Those are good questions. My view is the ceramic matrix composites have come a long way since like the late 90s. And a lot of that's because the fibers are more robust. And we have fibers that are reaching the commodity level. I still don't think we have commodity fibers. But the fibers being the reinforcement is going to define what we're able to do with that material. And the matrix developments have really just kept up with what's unlocking the capability of the fiber systems, or providing protection for those fibers, or providing a way to do matrix-dominated properties that would just be acceptable. So where would they go? I mean, obviously in propulsion areas, anything that's hot.
Yeah.
The necessity to get to hypersonics and have a large heat soak is going to necessitate higher temperature materials, and I think ceramic matrix composites have a play there. And then lower temperatures, exhaust wash structures. I mean, what we're seeing is, alpha case formation on titanium can be limiting in some cases, and so you can get more life, and we're being asked to get more life from our customers. And operate at higher stresses, so you have some fatigue things you have to worry about. So the fact that you're able to sustain the properties for such a long period of time at such a relatively high operating temperature is in favor of the ceramic matrix composites, but you have to do it smartly. So, the oxide systems are favored in the fact that in an oxidized environment they don't, whereas the non-oxide systems, silicon carbide-based systems, they always have that pesting phenomenon, so they might be terrific at 3000 F, but if you're dwelling for a lot of your cycle at 700 to 1500 F, then there's going to be that area where you're just not able to perform because of the rapid oxidation of your silicon carbide without having that protective layer. So there's a number of things you have to watch in the design for how to use the material appropriately. So I still think that the thermal protection still has a play. Structural materials, I'd say, leading edges, things like that, for the access to space and for the hypersonic applications, and then in propulsion and exhaust wash structures.
Yeah. Okay. Dr. Vaya, how does the shift toward unmanned aircraft and defense change material direction at the macro level? How is that influencing that?
I mean, that's a great question. We're very excited about the shift because we think it provides greater opportunity to try materials out, maybe going back to the X-15 days. The idea of, at the highest level, there is a reassessment of the balance between unmanned versus manned versus attritable systems with regard to achieving different capability means. And that is definitely shifting the paradigm towards more unmanned and more attritable based platforms. And from a materials point of view and a development point of view of those, what that means is much greater opportunity to try things out like we used to do in the past. Because of low lot numbers, quick, rapid turnarounds, ideas of systems that will only last for 5 or 10 years, not 50 years, is really creating, I would say, a new demand, a new pool in the aerospace community that specifically is an opportunity to insert new material space. So from a general point of view, I think it's a great opportunity for both materials and manufacturing because now there's new users, new capabilities that are a little less concerned with regard to a manned system and risk that are associated with.
Yeah, you can push the envelope on performance more.
A lot better.
Yeah, absolutely. Here's a question I really like. The panel talked about bad application development as hindering the adaptation of these new materials. How can companies improve their application development and make new materials and methods more valuable? What are examples of good and bad applications? Application examples. So, Mick, you want to start with that?
Yeah, so for me, it's about tying to design intent. One of the things, if you look at the way Department of Defense does acquisition, when a platform's setting up, we go into our tech development, whereas we're looking at all those low-level maturity materials or technologies in general, and what can we mature in time to meet our preliminary design review. At that point, you lock down your material, you lock down your manufacturing process, and it usually takes about 4 years. After a preliminary design review, we've actually look at our engineering and manufacturing development, so we don't consider manufacturing until after we've locked down both the material and the process. So there's for what I would consider good application development, we've got a structural problem in how we do that. That said, when it comes to material development, those platform folks that are looking at the low TRL materials, they've got 4 years to mature that. They expect the material guys to take 10 years. So you're off the boat right from the get-go. And so what happens to our material development folks? They're sitting on the outside saying, kind of guessing. They're looking at that horizon going, okay, what is going to be the application 10 years ago? And they start trying to look at what particular technologies they think they're going to be required and how they match up with it. And it's really not informed by true design intent. So good examples of this are in the armor world. We were putting a lot of trying to guess at what threats were coming down from our enemy, and then figuring out what material technologies would address those threats. The issue is we were working off that very direct threat, whether it was a ballistic threat or IED, trying to figure out solutions, and we weren't considering the actual application of, okay, now I've got to mount that onto a vehicle. It's going to go through vibrations. It's going to be in this kind of environment. And so there was some technology, and there's a cost associated with that. So we were developing some technologies that didn't meet our platform requirements.
Yeah.
And so having some design intent, whether it's how the environment the material is going to operate in, what the cost bogeys are, what the sustainment conditions are going to be. Having that information when you start the material development and tying those two together, I think is really important. And that's what makes the difference between a good development, applied development program versus a bad.
Okay, thanks, Mick. Let's see, I think we got time for one last quick question. What are the key factors in making composite materials as a whole more available to small businesses in the commercial aircraft industry, the way metal parts are done today? Is there an Alcoa of composites? Talk to SciTech or one of them. They probably think so. When I dial up the composite shop down the road, is there a place I can go to rapidly get parts and that type of thing? So I'll make a quick comment on that. Autoclaves are generally a big problem with that. One breakthrough that's really still, I'll say, an ongoing story is the out-of-autoclave composite activity. That does give the small and medium enterprises an opportunity to make parts, and that was one of the reasons why DARPA, invested in that, to open up that industrial base to allow composite parts to be more widely distributed and increase the competitiveness, if you will. But there's always that balance, right, of cost versus performance. Any other comments on that, or?
I mean, I can sympathize with it because a lot of people don't really look at the tooling involved with composites, and that can be a killer. So
Yeah. Yep.
Yeah, to me, I think you have to take a holistic approach to it and look at all the NRE and development costs. In particular, when you look at the speed at which platforms are being developed these days and new threats that occur, the ability to react quickly often is driven by your NRE ends up becoming the slow piece of that.
And the speed in which you need it.
Yep.
So there are more processes with the composites. One of the nice things about aluminum, as I always say, is you can make it so many different ways. You can use it for so many processes, and composites is getting to that point. But you got to have the performance has to really make a difference.
Go with it.
Well, I think that's it. We didn't get to quite all the questions. I think many of us will be available if you want to talk one-on-one after this session. So I thank you very much for the excellent questions, and I thank the panel for their excellent thoughts and sharing the ideas. Thank you very much.